Hi everyone. So today we're going to talk about a very special type of basically stress state that we're going to encounter, specifically thin-walled pressure vessels. So obviously this is important a lot when you kind of think about applications. You could imagine basically if you're kind of transporting oil, so pipelines, kind of those big basically propane tanks, but there's also kind of less obvious kind of thin-walled pressure vessels too. So a lot of cells can be approximated as basically thin wall pressure vessels. I have one of my favorite problems that you'll probably see come up on the problem set is basically a capsid or a virus. A virus, a biological material, can be treated mechanically as a thin wall pressure vessel. So we're going to see how that special stress state occurs and how we deal with that. But first, just some motivation. Unfortunately, we don't get to talk about this in class, but in Boston, there was basically this great molasses flood of 1919. So they had this molasses factory. It occurred in Boston. And again, I was there for 10 years at MIT for undergrad and grad. So in Boston. So this occurred basically on January 15th. January 15th. And basically what happened is this molasses factory, the kind of containers and the tanks that they were storing molasses, they exploded. Basically this whole flood of molasses ran down the street at 35 miles per hour. Unfortunately, it killed, so 21 people were killed. And it's in the north end. The north end of Boston is extremely popular. Now you'll go to Mike's Pastries. There's a lot of Italian restaurants there, but 21 people were killed, 150 were injured. So it's actually a huge disaster, not as funny as the name would imply. So does anybody know why this happened? Well, if you've ever lived in Boston, especially in the winter, one of the annoying things is kind of temperature fluctuation. So it went from below freezing, so it went from negative degrees, basically below 0 Fahrenheit, 0 F, to 40 degrees Fahrenheit in a matter of hours. So that obviously increased the pressure. The pressure vessels could not hold, and you get the result. So we want to make sure that as material scientists, we design materials so that this never essentially happens. So what we want to do is figure out, when can we make the thin wall pressure vessel approximation? How can we describe stress and strain in these scenarios? And how are we going to work with this moving forward? So a lot of things to do, but we'll tackle it one step at a time, just like always. So it's not as frightening as you might anticipate. So, and it's actually pretty fun. So pressure vessels. So when we're working with pressure vessels, we are going to look for this assumption and see if it is a thin wall. So, thin wall. What does a thin wall mean? Well, and there's kind of a couple conditions. So pressure vessels, one thing that we have to have is basically this delta P, this internal pressurized system. So we need to pressurize the material. There needs to be a pressure difference between inside and outside. So we have this condition of thin wall when we find that our R, the radius of our pressure vessel, is the ratio of R over T is greater than or equal to 10. So thin wall, we want to make sure that the thickness T, the thickness of our pressure vessel, is much less than R. So if we satisfy this condition, we can treat it as a thin wall, and typically we're going to be working with cylindrical pressure vessels. So first thing first, so before, all of this holds only when this condition is met. So whenever you're dealing with the problems, if you hear radius and if you hear diameter and you hear thickness, check and see, are we thin-walled first? If we're not, we're going to kind of talk about how we deal with that at another point. But that's going to be kind of your scenario here. Now, if we have a thin wall, so let me actually draw my pressure vessel really quickly here. Again, I always want to have my coordinate system in place. So here is my attempt at drawing a cylinder. Not too bad. You've seen my other horrible drawings, so this is a step in the right direction. So once you have this thin wall approximation, the problem reduces to basically a 2D stress problem. The reason being is that if you kind of cut open, if you kind of cut through the thickness, so again, this is a cylinder, so there's going to be kind of some in here. If you were to kind of make a cut in half, basically you'll see that there's no variation in the stress through the thickness of your material. So you could kind of just treat that as like a surface. So we are not going to have basically stress or strain effectively in that direction. There's no variation in the stress along that the thickness of your particle. So the thickness of your cylinder, excuse me. So what you end up with is we're going to have basically two types of stress. Longitudinal stress in this direction. And actually, let me change color so that we could be kind of clear on that. Let me redo this, redo that. So I'm going to have, let me go to red actually. So I'm going to have stress along this direction. So it's going to push out and push on the caps. We call this the longitudinal. And I'm going to have what's called a hoop stress or circumferential stress. So we'll kind of talk about that in a second. And that's going to go kind of along, it's going to kind of stretch kind of this, you know, this isn't a great kind of description, but it's kind of like stretching the skin around the hot dog. So it's stretching the skin. It's not going through the thickness of your material. It is kind of stretching around there. So the pressure is basically causing that material to stretch circumferentially. So circumferential, circumferential, or most often hoop. So let's kind of see and actually, you know, go back to kind of statics and draw a free body diagram. So if I want to figure out what's the circumferential stress, or actually let's start with a longitudinal. I need to kind of make a free body diagram. I need to make a cut in my material. Where am I going to make my cut? If I want to measure the stress in that direction, in the one direction, well, what I'm going to do is I'm going to make a cut transverse, 90 degrees. So when I cut out that material, if I'm looking at the longitudinal, I'm going to have now a material that looks like this. So it's going to be cut, and I'm going to have my cylinder, and it's going to go around here. And now, basically, I have kind of these two forces. Again, we want to free body diagram. We need to make sure that our forces sum to zero. So there's going to be some force that's kind of emanating from this little ring here, like this. And there's going to be some force, some pressure pushing in, kind of opposing that cut right here on the interior there. So let's actually go and take a step back and look at, actually we'll do the sum of the forces in just a second. And actually we'll do it right now. So this is the force from delta P. Actually, let me redo this here. So this force that's kind of opposing along this kind of interior ring here, that is going to be this longitudinal force, this sigma 1,1. Now, what's the area? We want to make sure for the longitudinal, our goal is to have the sum of the forces in the one direction be equal to 0. So if that's the stress kind of emanating, again, once we make that cut to kind of balance those forces, that is going to be sigma 1,1 times, again, a force. We know that stress is in units of force per meter squared. Force per area, so Newton per meter squared. We want to make the sum of the force being equal to 0. We need to multiply this by an area, a meter squared. So I want to make sure, I need to figure out what's the area that that force is acting on. Well, we assume it's a thin wall, right? So this thickness here, I'm going to draw it here, this thickness is really kind of almost negligible. So we're just going to say that the area it's acting on is going to be the circumference times that thickness. So it is just going to be this force times 2 pi r times t. And again, we assume that r, the radius is effectively going to be the same. You don't need to kind of think about the internal versus the external because that t is small. So our force in that direction is just going to be that, the stress times 2 pi r times t. Now, that is going to be opposed by, again, the pressure that's being exerted in the opposite direction. So the pressure that's kind of being forced internal here. So that is delta P. And again, delta P, that is in units of pascals or ATMs. But again, that same idea, newtons per meter squared. So we need to multiply by, once again, an area. Now, what is that area that it's acting on there? Well, that's just an area of a circle. So that is going to be that 2 pi r squared. Or sorry, excuse me, pi r squared. So pi r squared. And that's it. Now I could set that equal to 0. I could solve. and I find that my sigma 11, which is equal to my sigma longitudinal, is equal to delta P R over 2T. Very important kind of finding there. So again, let's kind of blow that up once more. So you can kind of see here, there's going to be the force emanating from along that ring here. So again, that's just going to be, that area is the area that this sigma 11 is acting on is going to be the 2 pi RT. And then the pressure that's kind of being exerted here along this circle, again, thin wall, you could just approximate that as times pi r squared, just that area. So yep, this is your kind of important, so we'll remember this in just a second. So now unfortunately I'm going to have to erase because we need to do the same thing for the circumferential or the hoop stress. So let's deal with that guy next, and I'm going to change color just to make sure that we know what's happening here. So when I change to blue, now where I'm going to make my cut for the circumferential. Well, again, transverse, right? So now it's a little harder diagram to kind of draw. I'm going to do my best here. So do this, and I'm going to draw this. Let's see how good I can get it. And then right here, this. Pretty decent actually of me. Again, I'm not an artist. I'm not sure we'll see the actual picture in a second. So that's kind of my best attempt here. So same idea. So we have some thickness here, T. We're going to call this distance here basically this delta X. So there's some thickness there. There's some basically delta X there. And we're going to call this right here, this distance, is going to be your 2R. So same idea. There's some force coming out once we cut that free body diagram. Again, this is just back to statics. So force coming out here. That force is what? Well, that's just going to be your sigma 2, So, excuse me. So we want to make sure now that the force, that the sum of the forces, sum of the forces in the 2 direction is equal to 0. So that is equal to sigma 2 times, what's the area this is acting on? Well, it's this rectangular region, right? So it's delta X times T, it's basically this area. Delta X times thickness, but there's two of these, 1, 2. So it's multiplied by delta X times T times 2. And then you could kind of imagine this area here, that's where the pressure is being exerted. So on kind of this square region right there. So that region is going to be 2R times delta X. That's it. So minus the delta P opposing times 2 times 2R, delta X. So you set that equal to 0, and you find that sigma 2, which is our hoop stress, is equal to delta P R, R over T, the radius. So this, I'm going to erase now. So hopefully, again, that was clear. And we'll actually take a look at kind of a better drawing in the notes in just a second. But this is an extremely important finding. So I'm going to kind of erase here, and we're going to kind of write this out a little bit clearer. So I'm going to do this. I'm going to clean up this diagram here. See that in just a second. Let me redo here, erase here. All right. So let me write out that again. So my hoop stress is going to be delta P R over T. My longitudinal stress is going to be delta P R over 2T. Now, this is a profound finding. So we just had, again, let me draw our coordinate system. So we know that the hoop stress goes like this. So this is going to be your hoop around kind of that circumferential. So this is sigma hoop. This is my sigma longitudinal. Your stress in that direction. So what do we know about the relationship between sigma hoop and the longitudinal? Well, we know that the hoop stress is twice the longitudinal stress. This tells us a lot about how this material should fracture if there's no kind of defects or any other stress concentrators happening in our material. The materials always fail basically where stress is the highest. They want to kind of release and get rid of kind of this this built up kind of strain energy as quickly and easily as possible. So materials will fracture, generally speaking, where the stress is the highest, again, as long as there's no other, they want to basically fracture along the path of least resistance. So if I apply a large stress kind of along, if I kind of stretch my material, you can imagine stretching it out here and here, how should this cylinder fracture? Where should the crack go? Should it look like, should it fracture along this or should it fracture like this? Well, if I'm stretching like this, pulling it here, it should fracture like this. This fracture would occur if, again, sigma L was larger than sigma H, or longitudinal. So this would hold true if sigma L was greater than sigma H. That's not the case at all. Again, in this scenario, if there's no defects, there's no stress concentrator. So you should expect to see a crack like this. And actually, if you go and look online, you'll see, again, for cylindrical pressure vessels, that is your common kind of fracture pattern there. So that is basically these kind of pressure vessels in a nutshell. But we could go a little bit step forward, a little step further when we're talking about kind of how to solve problems. So let's write out, since we know what's happening here, let's write out the stress and strain tensors in the system. So my stress tensor is going to look like this. What do we have here? Well, in the 1-1 direction, we have sigma L. Nothing else there. We have sigma hoop in the 2-2 direction, and that's it. Now, if I want to look at my strain tensor, again, primarily you're going to have, right here, you're going to look and want to calculate strain. It's going to be L 0 0 0 hoop 0 0 0 0. So if I want to calculate what is my hoop strain, again, you could just calculate that from using the expression we derived previously, right? So we introduced last time this expression, epsilon ij is equal to 1 over e times 1 plus nu sigma ij minus nu times sigma kk Kronecker delta ij, right? We know, sorry, I'm going to erase again. If we want to calculate the longitudinal stress or longitudinal strain, so we know that epsilon 1 is equal to epsilon L, which is equal to 1 over E times sigma longitudinal minus nu sigma hoop. That's it. Again, it follows from essentially your expression there. So that's all you have to kind of deal with. You could do the same thing for the hoop stress. And again, you could start to see and solve for whatever, you could be given a delta P, an R, a T. Again, you want to write down the equations and then go and kind of try to solve those. Again, just manipulate those equations. It's kind of, it's right there for your kind of picking. Now, one other last thing I'll leave you with. There is a really unique finding that you could do. And there's some characteristic ratios. So you can prove, and actually what you want to do, I want you to kind of take a look at it and think. Look at the ratio of, if you take the ratio of the hoop stress to the longitudinal stress. Take a quick second and see if you could kind of do that for me. Actually, let's do that together right now. So let's kind of write that. I'm going to take out and use Mathematica for a second, because you know that I love Mathematica. So I'm going to write out this expression, and you're going to see this kind of cool phenomenon happen. So I'm going to have to open my notebook and switch from my writing mode. So bear with me for a second. That wasn't too bad. So my epsilon hoop is going to be 1 over my Young's modulus times my sigma hoop minus nu times sigma L. And my epsilon L is going to be equal to 1 over y times my sigma L minus nu times sig h, where we also know that my sigma hoop is equal to del P times r divided by t, and my sigma L is equal to sigma h divided by 2. So let's shift enter that. I'm going to just suppress that output because it's not really super important. Now, let's see when I take the ratio of EH to EL. Let me fully simplify. Look at that. It reduces to an equation that is only depends on your Poisson's ratio. So the ratio of hoop to longitudinal strain just depends on nu. So if I'm dealing with metals, I know that my Poisson's ratio is 0.3. So my ratio of hoop to longitudinal strain is 4.25. If I'm dealing with polymers, 0.4 is 8. If I'm dealing with ceramics, it's 3. So again, this is a powerful relationship when you're dealing with lots of equations that you could kind of solve some of these problems really quickly by knowing that relationship, that ratio of hoop to longitudinal strain. So I hope that's useful. Hopefully it's useful it will definitely become useful in your problem set. And if you have any more questions, please let me know. Please be safe out there, and yeah, have a great day. Bye.